Today we're going to do chapter 10, day 5, talking about vectors in plane, looking at the geometric approach. So a couple things to know here. Scalars in general are measured with a single number. They're similar to a constant. Vectors themselves, they look like rays where you start at point P, that's the initial point, and then the terminal point would be Q. So the arrow tells you the direction, but one thing that's different between a ray and a vector is a vector only goes the distance P to Q. The arrow does not mean that it goes on forever. It just means that that's the direction in which that vector is going, okay? It is written as PQ, where the first letter is the initial point. The second letter that has the arrow on it is the end point, the terminal point. This is our component form. There's a couple forms here that we're going to look at. The component form is written as x comma y, kind of like a coordinate, but notice that there are two different symbols on the ends, not parentheses. And then there's a horizontal component that we can find in a vector. We can find that by doing the absolute value of the magnitude of the vector times the cosine of the angle. Vertical component would be, again, the magnitude of the vector and the sine of the angle, which leads us to this last part. If we're trying to find the magnitude of a vector, we're going to show you how it relates to the Pythagorean theorem, but you're essentially doing the Pythagorean theorem with the component form of that vector. Okay? So if we take a look here now down to vector addition, so if you have vector u and you're adding it with vector v, this is called head to tail. Okay? So the head of the vector goes to the tail of the vector. So the resultant vector, that's another term that we're going to look at, the resultant vector, u plus v. Well, if I went this way and then I took this way, when I add u and v, my resultant vector just says from that initial point, I actually ended up going straight there. Okay? The resultant force next to it shows you using the parallelogram law that essentially if I'm going from here, here, and I'm going from here, here, right, instead of head to tail, we can use the parallelogram law to move that u vector over here so that now I am head to tail, and then u plus v gives us that direct path that we saw in the previous problem. So if your given vectors right here are not head to tail, you can use the parallelogram law to make them head to tail so that we now have that direct path from the initial point on v to the end point on u. And that's how you get u plus v. So those are a couple initial concepts on vectors that we need to know and be able to apply. A couple navigational vocabulary there. Please read them. Have them available to you. Heading, airspeed, ground speed, v plus w or u plus v. This is the course, meaning this is the end of what we're trying to get. And then drift angle is another. So we're going to encounter those a little bit later. I started here a little bit early. It says we're trying to find the magnitude of these vectors. So in this case, we're doing QS based on the given coordinates they give up here. If we're starting at Q, going to S, there's our vector right there. So this is where we're going to talk about the magnitude. Well, if I make a nice little right triangle, right, and I find the magnitude of this part and the magnitude of this side, right, then the Pythagorean theorem would give me the length of that actual vector. So if we have 1 and we have 3, well, Pythagorean's theorem states x squared plus y squared equals c squared, and then square root both sides. So then you end up with the square root of 10. Okay? And our formula, again, that we just showed up top, sorry, it was a little higher than I thought, states that the magnitude of the vector can be found using that square root of x squared plus y squared. I just wanted to show you guys kind of how it relates to our right triangle Pythagorean theorem. Okay, but again, it only works if you have that right triangle, the x and the y values to be able to use that. So over here, getting a little bit more complicated here, we have QP, that's one vector, and we have QR, that's our other vector. Well, if we're trying to find the magnitude of these two vectors added together, remember it's head to head, right? So we can't actually use that yet, or sorry, tail to tail, so we can't use that yet. Instead, we have to use the parallelogram law. Well, if you notice, this vector goes down 3 units. So if I just move it, so it's head to tail, now I'm going down 1, 2, 3 units. And all we did was we moved that vector so that it's head to tail going 3 units down. So this is kind of like QR, but because it's in a different position, it's not labeled QR, but it again fills out that parallelogram law that we saw before. Okay, so now what we're trying to do is find the resultant vector from when we add those two. So from the initial Q to the end R. So that's our resultant vector that we're trying to find. Well, how do we get there? From this point to this point, we're going to go down 1, 2, 3, 4, 5, 6. So we have 6 as our y value, 1, 2, 3, 4, 5 as our x value. So then the magnitude would be 5 squared plus 6 squared. Square root of all that, you end up with the square root of 61. So you see there the initial magnitude formula that we have, right? Square root of x squared plus y squared. And then the ability to add two vectors together, making sure you go head to tail, and then getting the resultant vector from the initial point to the terminal point of that second vector. So this right here, this vector is QP plus QR. Okay, because we added the two initial vectors that we were given, QR and QP, we added them together to get that resultant vector right here. On the next page, if we take a look at number 3, again, all we're going to do is we're going to see the parallelogram law kind of in action. So we have G, the magnitude of G, they're telling us is 26.83. The magnitude of F is 4.06. And we're trying to find the magnitude of F plus G. We got to find the length of F plus G. Well, again, we got tail to tail, so we can move the F vector over to this other side. So now, if we're head to tail, we got F is 4.06. We got G is 26.83. Well, because this was a right angle, now we have a right triangle. And again, you can use your magnitude formula to find the magnitude of F plus G. So if we do that, we end up with the square root of 736.3325. So F plus G ends up being 27.14 newtons. So there's the length of F plus G. So some basic right triangle trig once you've recognized that F can be moved to the other side going head to tail so that we have the resultant vector in the correct spot. Now it's asking to find angle theta also, right? So that's angle theta right there. Well, again, thinking back to our right triangle trigonometry, here's our opposite side, here's our adjacent side. So we have tangent of theta equals 4.06 over 26.83. So then theta would be the tangent inverse of 4.06 over 26.83. Type that into your calculator. Just make sure, if you guys are using the Chromebook calculator, be careful and make sure that your mode is in degrees mode, because every time you open up your Chromebook, every time you open up the app, it resets it to radians. So make sure that we go ahead and switch it to degrees mode. So tangent inverse of 4.06 divided by 26.83. Type that in, you get 8.6, roughly. So this is 8.6 degrees. Taking a look at number 4, it's going to be very similar. Let's label what we know. So we know F is 8, we know G is 10, and we're trying to find F plus G. Well, again, if we're tail to tail, let's move vector G over to the other side of that parallelogram. So we have G equals 10 over here. Now, the other thing that they give us is they give us this full angle alpha right here. So they're telling us that that is 60 degrees. Now, if we're looking at this here, the first thing we want to do is recognize that this is not a right triangle, right? So we can't use that square root of x squared plus y squared formula because it's not a right triangle. So if I'm finding this side on a non-right triangle, that Pythagorean theorem approach is not going to actually work. So we can't use that. Instead, we need to think a little bit and recognize what kind of triangle we're looking at. Well, if I cover the rest of this up, right, it's a non-right triangle. The problem is we don't have any interior angles. You guys have some knowledge from earlier in this chapter on solving for an unknown side when you're given a side, an angle, and a side. So let's think. In order to find this angle right here, we know that parallelograms have consecutive angles that are supplementary. So if this is 60, then these two angles have to add to equal 180, right? Opposite angles are congruent, and then consecutive angles would then be supplementary. So we know that this angle is 120 degrees. So now that I have a side, angle, side, we can use the law of cosines to find f plus g. This is our other side. Let's call it x for now. So if we're using the law of cosines, we know x squared equals 8 squared plus 10 squared minus 2 times 8 times 10 cosine of 120 degrees. Plug that right side in. Again, make sure that you are actually in degrees mode. If you're in radians mode, you're going to get a different answer. So we get x squared is 244. Square root both sides. You end up with x, which remember we said is that resultant force, which is F plus G. So we're going to say F plus G is 15.62 newtons. Okay, so just a quick recap. They were giving us the full angle. We had to use consecutive angles in a parallelogram being supplementary to find this angle. And then we could use the law of cosines to find this unknown side. So now that we know this unknown side is 15.62, we know all three sides of this non-right triangle. We also have to find this other angle right here, which is theta. So again, if we're kind of blocking out this extra stuff, we're just looking at a non-right triangle like we did earlier in the chapter, but this time we have a side, side, and another side now. So we can use the other law of cosines. So this is the alternative formula, or you can use the original formula and say cosine of your angle equals 8 squared plus 15.62 squared. Oh, we're running out of space here. Let me move this down a little bit. Cosine of theta equals 8 squared plus 15.62 squared minus 10 squared all over 2 times 8 times 15.62. Plug that in. You get cosine of theta equals 0.8962, and then do the cosine inverse, and you end up with 26.33. Now I'm running a little bit quickly through these calculator parts because you guys already did law of cosines early in this chapter. If you have any questions on how to type them in or how we are working through this process of the law of cosines, please do not hesitate to ask your teacher for some assistance. Looking at number 5, find the vertical and horizontal components of the vectors given that the magnitude is 12 centimeters per second and the angle is 120 degrees. We just saw on the front page that the horizontal component is just the magnitude times the cosine of your angle. So it really is that simple. We know cosine of 120 degrees is negative 1/2. So negative 1/2 times 6 is going to be negative 1/2 times 12 is going to be negative 6 centimeters per second. So the horizontal component is negative 6 centimeters per second. The vertical component is going to be 12 times the sine of 120 degrees, which again, it says it on the front page. And then that one would be 12 times square root of 3 over 2, which you can plug into your calculator. You get 10.39 centimeters per second. And that is our vertical component. So those are pretty straightforward. As long as you know the magnitude of your vector and the angle at which you're working, you can find those two components. The last problem we're going to take a look at is number 6, where we're applying these to a real situation. So if we take a look, it says the heading is 30 degrees with an airspeed of 300 miles an hour. The wind speed is 25 miles an hour from 120 degrees. We're trying to compute the ground speed, drift angle, and course. Now, real quick, the ground speed is essentially the resultant force. Okay, so the heading that we're going to take a look at says the heading is 30 degrees with an airspeed of 300 miles an hour. Whenever we're talking about angles and directions, our angles are going to be measured from the north. So from the north, right, 30 degrees, so about here, 30 degrees from the north there, we are going at 300 miles per hour. We'll put this on the side, 300 miles per hour. That's the direction we're trying to go. And then there's a wind speed of 25 miles per hour from 120 degrees. So again, using the north, 120 degrees is probably about there. And this vector has the head at the origin, and it's going at 25 miles per hour from 120 degrees away. So this is the setup based on what we've seen. We're trying to find the resultant force. Okay, so from where we're starting, if we're trying to go this way at 300 miles per hour, but the wind is pushing us 25 miles per hour in this direction, where would we end up going? So we're going to try to use some vectors and vector addition to find the resultant force, and then we're going to find the drift angle off of our course and then the course angle. Okay, so the first thing we want to take a look at here is it says, hold on a sec, this is 120 degrees. In order to do our vector addition and find a resultant force, we have to have a head to tail setup. The problem is we can't start here and go up because we're actually starting at the origin. So what we first need to do is actually move this vector right here, the wind speed vector, so that the tail is actually at the origin. So we have here, if I move this vector over here, we can go ahead and do that. That wasn't a very good line. Right about there. This is still 25 miles per hour. That hasn't changed, but now we need the angle from the north. Okay, so a couple things here. If this is a full 120 degree angle right here, that's 120 degrees, we know that this smaller angle here is actually 30 degrees, which means vertical angles state that this one is 30 degrees, right? Well, if the full thing is 90, then we know that this is 60 degrees. This is extremely helpful because the next thing we want to do is we want to use the parallelogram law that we've been using to move this vector so that it is now actually head to tail, and we can find the resultant force right there. So this is the end game right there. Finding from the initial, if we're trying to go to the right in the northeast, and the wind speed is pushing us back towards the north, where is our resultant force going to be? Well, what's super helpful about this is if that's 60 degrees and that's 30 degrees, our parallelogram is actually a rectangle. This is really, really helpful because we're trying to find this resultant force, and because it's a right rectangle, we have a right triangle, we can actually use the square root of 300 squared plus the square 25 squared. You end up with 301.04 miles per hour. So that is going to be our resultant force, roughly 301 mph. That's our ground speed. Okay. Now the drift angle that they're talking about is the angle from the north. How far are we? The drift angle is actually how far we're going off course. So if we're going in this direction, right, we're going right here in the gray, how far are we drifting off course because of that wind, right? So from our heading, where we're trying to go along the blue, the green one is pushing us back. So how far is our drift angle? Well, if we look at this triangle, we know opposite and adjacent. We can do the tangent of theta is going to be 25 over 300. So then theta is the tan inverse of that. And you end up with 4.76 degrees. So if we're trying to drive or fly or whatever in the blue direction at 300 miles per hour, because that wind speed is 25 miles per hour from 120 degrees, our drift angle off course will put us 4.76 degrees off of our original direction. And the course angle is the direction we're actually going from the north, right? So we talked about the way we're going, the drift angle is from there. Well, if our initial angle was going to be 30 degrees from the north, we're trying to find the actual course angle. So if we were trying to go 30 degrees, right, 30 degrees minus what did our drift angle go because it's taking us back towards the north, 4.76 degrees, we actually end up with our course angle. So we end up with alpha being 25.24 degrees. So again, if we look at this in real time, in real life, we were attempting to go 30 degrees at 300 miles per hour. But then because of the wind speed pushing us back, we ended up going 300 miles per hour, but we ended up going only at 25.24 degrees from the north.